So doing a quick summary of our flowchart and our convergence tests. So let's go back to our flowchart. So the idea here is we look at our series and we determine, is the limit as k approaches infinity of whatever the rule is equal to 0? The answer is no. Then we know that the series is divergent. And ways you can tell it's no is if you can write it as a geometric series and show that the value of r is not between -1 and 1. That's one method. The second method is to do the divergence test and just using some algebraic tools to show that the limit does not equal 0. And then if we cannot prove the answer to that question is no, that kicks us over to this side. And so if the limit as k approaches infinity of whatever our series is does approach 0, and again, we could either get that from a geometric series where the r is between -1 and 1, or we start applying some different rules. And so in the previous videos, we looked at these infinite geometric series and the divergence test. I don't know why that says divergence test series. That should just say divergence test. Let's go ahead and fix that right now. And the p-series test. And so what happens when we run into a situation where we are able to show that the limit as k approaches infinity is equal to 0? So we've eliminated this, and we've eliminated that. Or when we do this, we are able to show that there's no way to put it in such a way that it is a geometric series. And for whatever reason, the p-series test fails because we're not able to put it in that form of 1 over x to the p. And so we need some other tools to evaluate, because otherwise we're limiting ourselves if these are the only types of series that we can evaluate. And so we're going to look at a couple different ways we can handle these. And so this is a summary of the infinite geometric series, the divergence test, and the p-series test. And so the next one we're going to look at is something called the comparison test. And we've approached this in two different ways in the past. And so the first way we approached this was when we first learned about the squeeze theorem. And we determined that if you were not able to evaluate an integral or some value, you were able to put it between two other values. And so the ones we looked at were a sub k, b sub k, and c sub k. And we said that if you can squeeze b sub k between a and c, that you're able to evaluate this in the middle as long as these two values squeeze together to the same location. And then we also looked at the comparison test for improper integrals. Again, we looked at those in a situation where I ask you to evaluate an improper integral, but for some reason, whatever the integral I gave you, you didn't know the rules, like you didn't know how to integrate it. And so what you were able to do is establish boundaries for that integral. And then if you could show that the value, and for improper integrals, we use 0 on the left and then some other value on the right. If you could show that that particular integral converged, then you knew that the one you started with also converged. And so we're going to use that same idea here with the comparison test for infinite series. And here's the more formal description of it. So the comparison test says, given two positive terms, so again, we're trying to restrict our focus to just terms that are positive. We don't want to venture into the negatives, which we will do later in this section 3b. And we also don't want to venture on this side of the y-axis, because when we're talking about terms of a series, you're talking about the first term, you're not talking about the -4th term. Like you don't have negative terms of a series. And so this says given two positive terms, and so we have a sub k and b sub k, the first thing you want to establish is establish a relationship between those two such that a sub k is less than or equal to b sub k for all values of k. And remember our notation here, k is a subset of the positive integers. And so the two ways we're going to look at this, the first is we have b sub k is on top because it's larger. And so if b sub k is this, and a sub k is this, it says if you can show that b sub k approaches some value, so we basically say that if that series converges, then a sub k must also converge. Now you will notice it doesn't necessarily mean that a sub k converges to the same location as your b sub k, but it just says that this value on the bottom, as long as it must stay less than b sub k, this series cannot approach infinity. It can't diverge. There's no way that it can. The only way it would diverge is if it could somehow overtake the b sub k, and we're saying that that is not possible. So it says if b sub k is convergent, then a sub k is convergent to a limit t. And again, the only thing we know about t is it is either equal to or less than s. Again, it does not have to be the same value. On the flip side of that is keeping the same relationship. So you have the a sub k on the bottom, and you've got the b sub k on top. What if you were able to prove that a sub k is divergent? So divergent means that this series keeps going and going and going and approaches infinity. Well, if b sub k is above it, there is absolutely no way that it can converge, because if some value below it is diverging, that's essentially pushing the b up to infinity as well. And so the second part of this is if a sub k is divergent, then b sub k is also divergent. And so one of the tricky things we're going to find is when I ask you to evaluate series using the comparison test, is you're going to have to determine whether the series that I give you is the a sub k or is it the b sub k. And you're not always going to know. And we'll talk as we get a little further into this section, how do you determine by looking at a series whether it converges or diverges? And so the example we're going to do with this, I'm not going to have you guys figure out divergence versus convergence. It basically gives you, well, actually in this one it does. I changed the wording a little bit. So it says establish whether or not the series here converges. So one of the ways you can look at this is try to look at the behavior of the graph and see if you can figure out what you think is going to happen. And that's one of the more difficult parts of convergent and divergent series is you're going to have to train yourself to be able to look at a series and determine whether you think it converges or diverges just by looking at it, and then using that idea to figure out if that's actually the case. And so what we're going to do right now is we're going to write an inequality. Now the problem we have is let's back up a little bit. We have 1 over 2 to the k plus 3. And right now, we don't know if this value is going to be the upper or the lower. And so we've got to figure out, based on what we know, whether it goes here or whether it goes here. And so one of the ways we can do that is we can simplify, similar to what we did with improper integrals, is how do you make a fraction bigger and how do you make a fraction smaller? And so if I look at this, let's say, for example, that I put this fraction here, and I ask you to come up with a fraction that is larger than 1 over the quantity 2 to the k plus 3. And so the ways you can do that, how do you make a fraction larger? And the two main ways you do that are you can either make the numerator bigger or you can make the denominator smaller. Now, one of the things we don't want to mess with too much is if we already have 1 or some constant up top, we probably don't want to do anything with this. But just to show you how we could do that, what if I bump that up to a 4? So 4 is clearly larger than 1. And so we get this relationship, which I would say is true. 1 over 2 to the k plus 3 is less than 4 to the 2k plus 3. But we run into a situation where it's not just enough for you to come up with a fraction that's larger. You have to somehow be able to evaluate this fraction. And so right now, if I give you a series where it's 4 over 2 to the k plus 3, I don't have any way to evaluate this the same way I didn't really have any way to evaluate this. It's not geometric. We could first off ask ourselves, what's the limit as k approaches infinity of this? And this is just the divergence test. So if you can show that it does not approach 0, then you don't even have to do any of this. But if I look at this, I have a constant over something that gets infinitely larger. So I know the limit is equal to 0. So I can't eliminate it. So it could converge or diverge. We just don't know right now. But this particular series, I can't do a whole lot with. And so one of the other options is to make the denominator smaller. And there's a very easy way to do it. How about we just get rid of the 3? And so by doing that, we have 1 over 2 to the k. And notice what I really did was I subtracted 3. And so you made the denominator smaller, which made the fraction bigger. And so right here, you have yourselves an inequality that says that 1 over 2 to the k plus 3 is less than or equal to 1 over 2 to the k. So this is true. And so now what we want to be able to do is evaluate this. And we've kicked out the plus 3, which it doesn't seem like it did a lot, but it actually did quite a bit for us. And so the way I'm going to do this is I'm going to take 1 over 2 to the k, and I'm going to rewrite it as 1 to the k over 2 to the k, because I know that 1 to any power is going to equal 1. And now that I've got that, I know that this also equals 1/2 to the k, because both the 1 and the 2 are raised to the k power. And so now what I have is I actually have myself a geometric. And so if I were to rewrite that as the sum from k equals 1 to infinity of 1 over 2 to the k, or 1/2 to the k, I know right now that this particular series converges. And I know that because going back to my rules here, I'm going to be using the infinite geometric series test. And it says if you have an infinite geometric series, as long as the absolute value of r is less than 1, or the way we said that, as long as r is between 1 and -1, I know my series converges. And so if I come back to this, that's exactly what I have right here. I've got an r value that's equal to 1/2. And since 1/2 is between 1 and -1, I know that this series converges. And so with comparison test, what we're going to find is it never acts by itself. And what I mean by that is within comparison test, you are going to be using the divergence test and infinite geometric series and p-series tests. So those first 3 tests are kind of wrapped into a package and used in other tests. And so now to kind of summarize here, what the comparison test says is, first off, establish this relationship, which we've done. So this is our a sub k, and this is our b sub k. The second is, if b sub k converges, which we just proved, then a sub k converges, which is this. Therefore, to summarize this, we've got the sum from k equals 1 to infinity of 1 over 2 to the k plus 3, I now know converges. And how do I know that? You say by comparison test. It is really hard to write with a mouse, so thanks for being patient. And we'll do a few more examples of these as we dig into the homework a little bit.